Okay, so this is the 40th lecture and the last lecture of this course. Here in this lecture, whatever fundamentals that we have done so far, we look at the applications of those fundamentals. So, the first very important application is how to harden surfaces of materials, where particularly the components made out of that material may be involved with a lot of wear, and how to increase the wear resistance basically involves hardening of surfaces. So, surface hardening is the first application let us look at, and in surface hardening there are many techniques, and we are not going to in this lecture going to go into several techniques, but we will look at one particular technique of surface hardening. And what is the objective of surface hardening? Is to form a hard surface for improving wear resistance of moving components. And you just want to harden the surface while the interior of the component or the core of the component is kept relatively soft, so that overall the component has a high toughness and high impact resistance. This is particularly useful for applications in the automobile industry, where gears are involved, camshafts are involved, and also in many other applications. As you can see, couple of illustrations here. This is a picture of a camshaft which is subjected to a lot of wear during its operation, because it is used in timing of the engine. And here is a gear which in which there is a lot of wear that could take place. So, you want to harden the surface of the teeth of the gear, so that you can improve the life of the gear. Now, as I said, there are many ways of doing this. One specific method of doing this is using diffusion. Through a process of diffusion, one modifies the chemical composition of the surface, so that the surface becomes harder. It is very commonly used in steels. In fact, one of the first hardening techniques was this only for steels. So, what you do is, through diffusion you introduce some hardening elements like carbon, nitrogen and boron in the surface layer. So, what you have done is you have changed the chemistry of the surface layer, while at the same time keeping the core at the same composition. So, for example, if you have introduced carbon in the higher carbon content in the surface, then one can use transformation hardening, heat treatment, through which on the surface you get martensite, while the core is kept soft with a structure like ferrite and pearlite. This is illustrated here as follows, that here is a component. The surface of this component here is exposed to an atmosphere of high carbon concentration, and of course, this component is kept at a high enough temperature, so that diffusion of carbon can take place from the atmosphere into the material in the surface layers. So, what you see, eventually a high carbon content surface layer is formed, while the rest of the material is kept at low carbon. Now, as a result, the transformation kinetics have been altered at the surface as compared to the interior. How is it altered? Well, if you look at the transformation diagram, a small transformation diagram that I have schematically shown here, the temperature versus time CCT or a TTT diagram here. As you increase the carbon content, the kinetics of the transformation to ferrite and pearlite slows down. As a result, the C curves of the transformation diagram, these C curves that you see here, they are shifted to the right. So, what happens is, for if you now heat treat this component by taking this component to the austenite region, where now everything has become austenite, and then you cool this component. In one case, in the interior part, the cooling rate that is produced intersects the ferrite pearlite curve. So, this is the ferrite curve and this is the pearlite curve. As a result, the microstructure that you would get in the core would be ferrite and pearlite. On the other hand, the surface layer which have a higher carbon content, their transformation diagrams would have been shifted to the right. Then for the same cooling rate, those cooling rates may not intersect the ferrite or the pearlite seekers, they would directly cool down into the martensite region, producing a hard surface consisting of a martensitic structure, as illustrated here. So, in the core you have a ferrite pearlite structure, and in the surface layers you have a martensitic structure, a hard surface is produced. So, you have a hard surface in the end with overall toughness of the component being still kept high without losing the toughness or the impact resistance of the components. So, for example, camshaft and gears come under a lot of impact loading, so they can still sustain those, while at the same time the wear resistance has been increased through surface hardening. Now, what I will do is I will take up a specific case of surface hardening in a steel, where we will look at a problem and see how we can estimate how much time, at what temperature we should subject this component so that we get a certain thickness of the hardened layer. So, let us look at this on the board. So, surface hardening is specifically by a process called carburization. In this, as I have already explained, that you subject the steel in this specific case to an atmosphere containing a high carbon concentration. So, let me first outline the problem and then solve it. So, there is a plain carbon steel out of which some component has been made, whose composition is 0.25 weight percent carbon. Now, this is the carbon content in the surface of this component has to be increased, or this has to be subjected to a carburizing treatment. And what is involved in this carburizing treatment? We will subject the system to that will do carburization at 1000 degrees centigrade, so that at a depth of 1.5 millimeters, the carbon concentration should be increased to 0.5 weight percent carbon. So, what we want to do is that at a depth of 1.5 millimeters, we want to double the carbon concentration from 0.25 to 0.5 weight percent. In order to do this, the surface concentration through that carburizing atmosphere is maintained at 1.2 weight percent carbon. So, typically a carburizing atmosphere would be a gaseous atmosphere kept at 1000 degrees centigrade, so that the surface concentration throughout the carburizing treatment is kept at 1.2 weight percent carbon. And what do we want to find out? Well, we want to find out the time required for this treatment. That is, the time required to increase the carbon content at a depth of 1.5 millimeters from 0.25 weight percent to 0.5 weight percent. So, this is a simple diffusion problem of carbon and of carbon atoms diffusing into the steel. One would also require, in order to solve this problem, the data for diffusion. So, one can keep diffusion data. So, at 1000 degrees centigrade the steel will be in austenite. So, we require diffusion data for carbon diffusing in the austenite structure. So, for that D0, the frequency factor is 2.3 into 10 to power minus 5 meter square per second. The activation energy for diffusion is 148 kilojoules per mole inverse. So, let me illustrate this problem by drawing a diagram. So, I have a component made out of this steel of 0.25 weight percent carbon. This surface of this is exposed to an atmosphere of high carbon concentration, such that the surface concentration Cs is kept at 1.2 weight percent carbon. The initial concentration of carbon, we call it as C0, is kept at 0.25 weight percent carbon. So, at time t is equal to 0, everywhere it is 0.25 weight percent carbon. After some time t, we will have carbon diffusion into the material and we will get a profile something like this. So, this is at some time t, and in fact, I want to find the time t for which at a depth of 1.5 millimeters the concentration becomes 0.5. So, I want to basically find the profile at time t, which gives me this particular concentration at this particular depth. Now, if you recall from the last lecture, I can write the concentration profile Cxt, concentration as a function of distance and time, as a constant capital A plus another constant capital B times the error function x divided by 2 root dt. Let me put a boundary condition that at x is equal to 0 at any time t, the concentration is Cs, the surface concentration fixed by the atmosphere. Then there is an initial condition I can put at t is equal to 0, Cx0 for x greater than 0, the concentration everywhere is the initial concentration of the steel C0, which is 0.25 weight percent. If I put these this boundary condition and the initial condition, well, if I put the boundary condition C0t equals Cs into this expression, well, when I put x is equal to 0, error function of 0 is 0. So, hence the constant A is simply Cs. I put the initial condition Cx0, this should be C0. So, when I substitute in this t is equal to 0, I get error function of infinity. Error function of infinity is 1, hence C0 is equal to A plus B. From this, I will get B is equal to C0 minus Cs. Substituting A and B into this expression, I will get Cxt is equal to Cs plus C0 minus Cs times error function x divided by 2 root dt. So, this should enable me to solve the concentration profile for any x and for any t, and let us see how we can do this for the specific problem at hand. So, let us look at rewriting this expression as error function x divided by 2 square root dt equals Cxt minus Cs divided by C0 minus Cs. Now, let me substitute that I want at some depth, at a depth of 1.5 mm, I want a carbon concentration of 0.5 weight percent. So, therefore, for Cxt, I will put 0.5 minus the surface concentration is fixed at 1.2 weight percent. So, I will write 0.5 minus 1.2 for the numerator, and in the denominator C0 is the initial concentration of the steel, which is 0.25 minus Cs, which is 1.2. So, on solving this, I will get 0.7368. So, error function of x upon 2 square root of dt should be equal to 0.7368. In this, if I know x and I can find d from the data given from d0 and q, I should be able to find time such that the error function of this quantity should be equal to 0.7368. Now, how to do this? We will have to go to what is called as the error function table, where there are table of values given, and from that table one should be able to obtain that for error function to be equal to this, what should be this quantity, and let me call this quantity as z. So, I can write error function of z is equal to 0.7368, and I need to find what is z. So, if I go to error function table, let me just do this. What you see here are for different values of z, I get what is the error function of z. So, for 0 it is 0, for 0.1 it is 0.1125, for 0.5 it is 0.5205 and so on, and as you can see that as z is increasing, the error function values are also increasing, and obviously for large values of z it will be very close to 1. Now, for the specific value in hand of 0.7368, if I locate this, I will come here. That 0.7368 lies between these two values as highlighted here. Therefore, Z would be in between 0.75 and 0.80. So, what we need to do is we need to do a linear interpolation. So, what I have is essentially a value of Z and error function of Z. So, I have for 0.75 from the error function table, it is 0.7112, and for a value of Z 0.80, I have an error function value of 0.7421 from the error function table. So, this I have obtained from the error function table, and 0.7368 lies in between these two, and hence Z should also lie between 0.75 and 0.80. So, I need to then do a linear interpolation to get the value of Z. How to do this linear interpolation? Well, let me just do this little exercise, that let me take these two values of Z and error function of Z. Let me say this is the Z and this is error function of Z. So, I have for Z1, I have the error function value to be, let me call it as E1. For Z2, I have an error function value, let me denote it as E2, and I join these 2 points with a straight line. Somewhere now, if I want to find an error function value in between, designated as E for a given Z. So, knowing Z1, Z2, E1, E2, if I know Z from linear interpolation, I should be able to get E. If I know E from linear interpolation, I should be able to get Z. So, this we can write. So, the slope of this line can be written as E2 minus E1 divided by Z2 minus Z1, and let me call that as M, the slope. This is also equal to E minus E1 upon Z minus Z1. Hence, I can write E is equal to E1 plus M times Z minus Z1. So, if I want to find at some Z in between Z1 and Z2, what should be the error function value? So, I will first get the slope from here, put the value of Z in this E1, Z1 and the slope value, I will get E. Or I can also write for Z as Z is equal to Z1, rearranging these terms, 1 upon M times E minus E1. So, now if I know E, the error function value in between E1 and E2, then I would be able to compute what should be the Z value. So, using this particular relation, I have this data and I know error function value in between these two. So, I should be able to get a corresponding Z value, which turns out to be, so first let me calculate the slope M, which is simply E2 minus E1. So, it is 0.7421 minus 0.7112 divided by 0.80 minus 0.75, and the slope turns out to be 0.618. From this slope, then I can get the Z value as Z1, which is 0.75 plus 1 upon the slope. So, 1 upon 0.618 multiplied by E minus E1. So, E is this, the error function for which I want to find Z, 0.7368 minus E1, which is 0.7112. This gives me a value of Z as 0.79. So, now I know what is Z, and Z itself is equal to x upon 2 square root of dt. X I know given in the problem at a depth of 1.5 millimeters. I need to find what is the diffusion coefficient d at 1000 degrees centigrade at which I am doing carburizing. So, now let me also calculate what is d. So, diffusion coefficient d is equal to d0 e to power minus q divided by RT. Now, let me write down what is d0. d0 is 2.3 into 10 to power minus 5 meter square per second multiplied by exponential E minus what is Q? Q is 148 kilojoules per mole. Convert the kilojoules into joules. So, it is 148 into 10 cube divided by R, the gas constant, which is 8.31 joules per Kelvin per mole, multiplied by the temperature at which I am doing the carburizing, and I am doing it at 1000 degrees centigrade. I need to convert this 1000 degrees to Kelvin, and so I will write it 1000 plus 273. So, 1273 becomes the temperature. This gives me the value of the diffusion coefficient as 1.93 into 10 to power minus 11 meter square second inverse. Now, with this value, so I now know in this, I know this whole quantity is equal to Z, which is 0.79, X is 1.5 mm. Now, I know what is the diffusion coefficient, so I should be able to find the time. So, let us find this. So, Z is equal to X divided by 2 square root of dt. I will substitute for Z as 0.79, substitute for X 1.5 mm, convert this to meters. So, 1.5 times 10 to power minus 3 divided by 2 divided by square root of d. D we have calculated just now as 1.93 into 10 to power minus 11 multiplied by time t. From here I will get a time of 46503 seconds. Convert this into hours, so divide this by 3600. This gives me that I require a carburization time of 12.9 hours or almost 13 hours. So, in order to get the carbon concentration up to 0.58% at a depth of 1.5 mm, I will need to carburize this component for almost 13 hours. Now, suppose I were to get the same, I wanted to get the same depth, not at one, I wanted to get the same concentration of 0.58%, not at a depth of 1.5 mm, but at double the depth at 3 millimeters. So, if I double the depth, how much time it would require? Well, I just have to look at this. If I double the depth, that means x is becoming 3, and in order to get the same concentration of 0.58%, the value of z would still remain as 0.79. Hence, if I double this depth, the time will have to be increased by a factor of 4, which would mean time would become 4 times 12.9 hours, and it would become, so for if x is equal to 3 millimeters, time required, x is equal to 3 millimeters at which the concentration should be 0.58%, time will become 4 times 4 into 12.9, and that would take me to almost 52 hours, more than 2 days of carburizing. Similarly, I leave it to you that if I double the time, then at what distance x I will get a carbon concentration of 0.58%. I will give you the answer to this. The answer to this is 2.12 millimeters, and you can work it out just the way we had worked this out, that if I double the time, what is going to happen to x for the same z value of 0.79. So, with this I will close discussion on surface hardening, a very important application, and let us move to another application, this thermomechanically treated steel bars for building construction. So, they come in various diameters. One particular diameter that is used is 25 millimeters, and they come in also various grades. This particular grade, which is grade 500, has a carbon content of 0.38%. Now, in this, if I look at the transformation diagram, then this is the transformation, it is just a schematic, it is not specifically drawn for this particular composition, where this is the ferrite C curve, these are the pearlite C curves, and out here you will have bainite. Now, what you want to do is you want to create a hard surface outside while a soft core inside, but in this we will not do any carburizing. What we will do is, or what is actually done in the industry, is that these steel bars are heated into to the austenite region, and then they are quenched. The surface is quenched in such a way that you have different cooling rates on the surface and the core. Obviously, cooling, if I spray water on the surface of these bars, the cooling on the outer surface region would be much faster than the cooling in the interior region. And in fact, the cooling is so controlled that in the rim region or the surface region, the cooling curve is given by this, while in the core the cooling is lot slower. As a result, you can very clearly see that in the surface layer the cooling does not intersect any of the C curves, hence no ferrite, no pearlite is formed on the surface, only martensite is formed, while in the core it cuts the ferrite curve, so you get some ferrite, it also cuts the pearlite C curve, so you also get pearlite. So, you get a ferrite pearlite structure. In fact, if you look at, you will get a gradation of structure right from the surface to the core, and these are the kind of microstructures you get. Right at the rim, it is a martensitic kind of structure, and towards the core it is a ferrite pearlite structure. So, as a result, you have a hard surface outside and you have a soft core inside, and if you measure the hardness of this right from the rim to the core, this is the kind of hardness data you will see. You can ignore the, just look only at the blue curve, and ignore the other curves because those are curves that are drawn for other treatments. So, just the blue curve, which is after this kind of a treatment is given to the steel bar, you have high hardness toward the surface, then the hardness drops, becomes minimum in the center, and then it starts to increase again. So, this is another example of modifying the surface, but in this no chemistry is altered. Another example is heat treatment of wheels for the railway coaches. So, these are photograph of some real wheels, and here again we try to make some modification to the surface, so that the rim has a somewhat different structure compared to the core, but here we do not produce any martensite. In fact, so in this the hot wheel, which is in the austenite region, is subjected to water spray all around the rim. As a result, the cooling curves that you get are this kind. These wheels are very massive, so the even at the surface the cooling is not as fast as it was shown in the earlier case for steel bars for construction. So, both the rim as well as the core cut the ferrite as well as the pearlite C curves, but the rim has a lot faster cooling. As a result, what you get is finer microstructure in the rim as compared to the core. Remember that in one of the lectures we had discussed that if you go down relatively low in undercooling, then you can get high nucleation rate but very small growth rate. As a result, you will get a much finer structure. So, you end up with finer ferrite grains in the rim and a finer pearlite lamellae, and you again get a ferrite pearlite structure everywhere. So, but then the pearlite lamellae, if they are very fine, then they can produce very high wear resistance, and this is what you want for these railway wheels. Now, one final application and an extremely important application is precipitation hardening. In precipitation hardening, it is also termed as age hardening, and it is perhaps one of the most important metallurgical discovery of the 20th century, and which changed the way materials got used, and in fact it enabled aluminum alloys to become very useful engineering materials. So, early applications of precipitation hardening was in the aluminum alloys, and it is considered as an accidental discovery. So, there was some work going on with aluminum copper alloy of a certain composition with some magnesium and manganese. This alloy was quenched from a temperature above 500 degrees centigrade. Above 500 degrees centigrade, this particular alloy is a single phase alpha, which has a face centered cubic structure. It was then quenched from that, and as a result the high temperature microstructure was retained. But then it was noticed that the hardness continued to increase with time. Of course, it took several days for the hardness to increase, and in fact the material was aging and getting harder. And in fact, it was such an amazing discovery that immediately it had commercial applications, and the particular alloy was named as duralumin. Even today this particular alloy is used extensively. So, duralumin quickly came into commercial use. Of course, hardening behavior remained a mystery for quite some time, as the microstructure and optical microstructure showed no change. So, people did not know for quite some time what was happening to the material. And now, just very briefly, we will discuss what is happening in precipitation hardening. So, this is going to be a brief introduction to precipitation hardening, in fact very, very brief. So, let us consider this aluminum copper alloy and specifically consider aluminum 4 weight percent copper alloy, which is called as dura-alumin. If I look at the phase diagram for aluminum copper, or part of the phase diagram, so this is aluminum weight percent copper, so this is about approximately 55 weight percent copper here. This point is about 5.6 weight percent copper. Out here is 33 weight percent copper. If I label the phases, this is liquid, this is alpha plus liquid, this is a phase called theta plus liquid, this is theta, out here is alpha plus theta. Theta specifically is Cu Al2 intermetallic. If I take 4 weight percent alloy, which may be somewhere here, and take this alloy at some temperature T inside the alpha phase. So, I start with a single phase copper 4 weight percent alloy. If I start to cool down, then what should I get? Well, I start off with the alpha grains, and if I keep cooling down, maybe I just cool down to, let us say, some temperature T1, which is high enough temperature for easy diffusion to take place. Then what would happen is the theta phase would start to precipitate on the grain boundaries. And eventually I will get alpha and theta in equilibrium as dictated by the phase diagram at that temperature T1. So, this is for small undercooling. But if I can also say that at T1, if I take this, then there is a supersaturation of alpha of a certain amount, and this supersaturation then has to dissociate and form the theta phase. So, this is for small supersaturation of alpha. However, if I go down to a much lower temperature, say like T2, the supersaturation is much larger, but the temperature is also very large. The temperature is also very low. As a result, now I have a much larger supersaturation, but the material cannot directly, the theta phase cannot directly precipitate, because the energy hill that is there for nucleation of theta to occur is very large, or delta G star is very large. And why is it very large? Particularly also because gamma alpha theta, the interface energy between alpha and theta is very large because of the very different crystal structures of alpha and theta. Alpha is face centered cubic while theta is orthorhombic. Hence, direct precipitation of theta does not become possible. So, what happens in this material? First, clusters form of copper rich clusters form, and the sequence of precipitation of theta, these is as follows. These clusters, copper rich clusters, are what are called as GP zones. So, these are copper rich clusters. Eventually, they transform to another metastable phase theta double prime, and this theta double prime decomposes to theta prime, and eventually it forms the equilibrium theta phase. So, theta forms in these steps. But the whole idea of this over here is that when you go down to such a low temperature, you have very fine precipitation everywhere because of the high driving force, not just at the grain boundaries. These are very, very fine particles which are cannot be observed in an optical microscope. One will have to go to a transmission electron microscope to see this precipitation. These very fine particles become obstacle for dislocation movement. As a result, you have a very significant increase in strength, and that is what is called as precipitation hardening. These kind of transient phases forming before the final equilibrium phase is formed is also observed in many other age hardenable alloys, in many other aluminum alloys themselves. They are also observed in iron copper, copper iron, copper titanium, etc. So, this is quite a general sequence where metastable phases form during precipitation, which give you precipitation hardening. And finally, what would be the practical steps involved to produce precipitation hardening is actually very, very simple. 3 steps that are required to produce precipitation hardening. You do not have to take the alloy to this temperature and then quench to T2. What you do is, as step 1, you solution heat treat, at T, so that everything is single phase, everything is solutionized. Then step 2, quench to room temperature. As a result, the high temperature alpha phase is retained with a very high supersaturation of copper in aluminum. And the last step, step 3, is the aging step, that you age at a specific but low enough temperature so that you get fine precipitation. Many of these alloys will actually even precipitate at room temperature, but they may take a long time for that precipitation to occur. With this very brief introduction to precipitation hardening, which is an important, very, very important application of what we have done, I bring this lecture to a close and as well as this course to a close. Thank you.